All right, given that x sub 1t of this is equal to this vector, is a solution of the system of differential equations x prime equals some matrix x, find another solution x sub 2t of the system such that x sub 1t and x sub 2t are linearly independent. So looking at this question, the fact that it gives us one of the solutions to the system here, this x sub 1t thing, and then it's asking us to find another solution x sub 2t that's linearly independent. And so the fact that they're mentioning this tells me that this system is going to have a case of repeating eigenvalues or defective eigenvalues. Because usually in normal cases, the two eigenvectors that you come up with, they're going to be, when you come up with your solutions, they're going to be linearly independent by default. But when you have repeating eigenvalues, you have to do a couple of additional steps to to make linearly independent solutions. And so looking at this solution, we can deduce that the eigenvalue of this system is going to be lambda is equal to 4 with a multiplicity of 2. So 4 and 4. Um, and so this saves us a little bit of time because we don't have to compute the actual eigenvalue. You can if you want to, if you're not convinced anyway, by just taking this determinant. So the determinant of a minus lambda I, and set that equal to 0, and then solve for lambda, and you'll come up with lambda. The eigenvalues for this system is going to be 4 and 4. And so the cool thing is also it already gives us one of the solutions, and so we can use that to come up with the second solution. Because usually once you find your eigenvalues, you plug the eigenvalue back into this matrix where you have I guess in this case it would be 3 minus lambda, negative 1, 1, 5, and 5 minus lambda like this, multiplied by x sub 1 and x sub 2 equal to 0, 0, and then from here you can come up with an eigenvector. But in this case, we have to do something a little bit different. So the first thing I'm going to do is what you'll notice is for repeated eigenvalues, instead of doing that process, the first solution, you just follow this process of doing this x sub 1, x sub 2 thing equal to 0, 0, and then coming up with an eigenvector. And when you do that the first time, you'll come up with the solution given here. But we don't have to compute that because we can actually isolate what the eigenvector, one of the eigenvectors is from the solution. That being I'll write it down here. So we know that x sub 1t is equal to e to the 4t over, and then negative e to the 4t like this. If we take out the e term and split it up, we can find that the eigenvector for this solution is 1 and negative 1. And so now that we have this eigenvector, we can use this to come up with our second linearly independent solution. And so to do that, instead of finding an eigenvector by setting this equal to 0, 0, what we're going to do is we're going to do the same process of 3 minus lambda, negative 1, 1, 5 minus lambda times x sub 1 and x sub 2, and set that equal to this eigenvector instead, like this. And then from here, the process is the same. Come up with set up an equation. But before we do that, let me also plug in let me plug in the eigenvalue. So we know that the eigenvalue is equal to 4. So when we plug in that in for lambda, we end up with negative 1, negative 1, 1, and 1 times x sub 1 and x sub 2, which just equals 1 and negative 1. And I'm going to use the bottom row for this just because I like having positive numbers. It's just my own personal thing. So when you do that, you end up with x sub 1 plus x sub 2 is equal to negative 1. And the process of finding the eigenvector from here is the same as the normal case up here, where you just pick two numbers that aren't 0, 0, and 0 that satisfy this equation. And to make things simple for myself, but the thing is, that doesn't mean that you can't have 0 as one of your numbers. As long as both of your numbers aren't 0, then you can have 0 as one of your numbers. So I'm going to actually do that. So I'm going to set x sub 2 equal to 0, and that's going to make x sub 1 equal to negative 1 by default. So our second vector that we come up with is going to be negative 1 and 0, like this. And so now we can come up with the second linearly independent solution. And so to do that, the process of finding that would be where you have your e term, so e to whatever your eigenvalue is, in this case 4. And then this is where things are going to start to get different. Instead of just plugging in this eigenvector that we found in and making that the solution, we can't do that. And the reason why is because when another thing you have to do, rather than just coming up with two solutions that are linearly independent, you have to make sure that they satisfy the original system, that being x prime equals ax, where a is this matrix. You have to satisfy this while also having linearly independent solutions. And if you plug this vector in and just attach it to this if you just attach this vector to this e term, it'll be linearly independent with the first solution, but it won't satisfy this. And so there's another thing that we have to do. And what we have to do for that is we need to multiply the first solution's eigenvector, so this, by t. And so that will give us a compound term where we have t times the first eigenvector from the first solution. And then from there, then we add this vector to the end, like this. And doing this will give us a linearly independent solution while also satisfying this. And so from here I can simplify things down. And so we can find that our second solution is going to be equal to x sub 2 of t is equal to e to the 4t times t minus 1 and negative t. Because that's just a 0, so it's just t plus 0, and just get rid of the 0. And so yeah, so now we have the second solution. And so from here we can pick an answer. And looking at these answers, none of them actually match what I have here, but I know that the answer is going to be E, because E is actually equivalent to what I have here, and I'll show you why. So what you'll notice is the reason why E is going to end up being equivalent to our solution here is because when we recall that when we were finding our second eigenvector, so when we found this vector, we had to pick two numbers for x sub 1 and x sub 2 that satisfy this equation. And it can be any two numbers so long as they're not 0 and 0 like I mentioned. And so in my case, I chose 0 and negative 1, but E, they chose a different set of numbers that still satisfies this equation. In this case, if you split up this solution, this solution is equal to e to the 4t times the original eigenvector of 1 and negative 1 times t plus negative 2 and 1. And so what you'll notice is this answer uses negative 2 and 1 as the numbers, whereas I use negative 1 and 0. But when you plug in negative 2 and 1 into this equation, it still satisfies it, because negative 2 plus 1 equals negative 1. And then, as well as my case, negative 1 plus 0 equals negative 1. And so basically, technically speaking, there's infinite different possible solutions depending on what numbers you choose. And this exam just decided to use different numbers. And so that's why E is going to end up being equivalent to my solution over here.